Alright, so last time we've discussed about continuous probability distribution, specifically on the continuous random variable and the expected value. Now we're going to discuss today is about normal distribution. Okay, when we say normal distribution, just a brief introduction of this, it's the most important, or should I say, one of the most important continuous probability distribution in the entire field of statistics because we use it in research, engineering, and other industrial and somehow commercial purposes. So the graph of the normal distribution is called normal curve, wherein somehow it's a bell-shaped curve because from the idea of having a bell, if you've seen a bell illustration or even an actual bell, somehow similar to that, the illustration or somehow the physical appearance of the curve. Okay? And then approximately, it describes many phenomena, just like I've said, in industry, research, and nature. Errors in scientific measurements are extremely well approximated because most of the time, if we're going to use the normal distribution, could actually see errors in the normal distribution. If you still remember the outliers wherein the data that are really far, or should I say, having a great difference with the data collected, no? That means maybe at some point the data that has been collected are are influenced, no, by the other factors such as human error. So in normal distribution, we could actually see or we could actually approximate what we call errors in scientific measurements because we could actually see in computation later on that uh, these errors may exist or these errors have been eliminated before or prior the computation. Okay? So in 1733, Abraham de Moivre developed the mathematical equation of the normal curve. So from that concept, in 1800s, Carl Friedrich Gauss developed, or should I say, uh, derived the equation of study of errors in repeated measurements of the same quantity, wherein the normal distribution is referred as Gaussian distribution in respect to Carl Friedrich Gauss. Because from the idea of mathematical equation of the normal curve of Abraham de Moivre, he developed or formulate or study the errors in repeated measurements. Okay, in the life of um, Gauss is from 1777 to 1855. Okay, so this is the figure or illustration of the normal curve. So as you can see, we have the mean. So these are the ones that we compute usually in our subject, specifically last time, that we compute for the expected value or the mean. And then we also have the standard deviation or the measure of the spread of the data from the normal curve. So in order to compute what standard deviation, we have also to find first the variance. Okay. So from variance, so we could actually get the standard deviation by the root of or the square root of that variance is the standard deviation. So standard deviation is equal to the square root of the variance. Okay? So from the idea of the normal curve and normal distribution, we could actually have the density of the normal random variable or the equation or the function for the density of the normal variable. So n here is equal to 1 over square root of 2 pi multiplied by standard deviation or sigma multiplied by e raised to negative 1 over 2 sigma squared or the variance multiplied by x minus mean squared, where x is ranging from negative infinity to infinity. So basically, it is a continuous probability distribution from that concept of or the value of x or what we call the interval on the values of x. Okay, so from this equation, we could actually derive other factors, or should I say, the computation that we're going to use in analyzing the normal distribution or the normal curve. Okay, so as I said a while ago, this is the normal curve or the illustration or the basic concept of the normal curve. We have the mean and the standard deviation. So in instance or in different instances, we have this kind of normal curves wherein your standard deviation are the same or equal, but their means are different. So in this case, mean sub 1 is less than mean sub 2. So this will be the illustration for that. As you could see, now we could actually see that there's an intersection point between two normal curves. Okay, I will hatch this one. So in this hatched area, we could actually see scores or values or what we say probability in relevance to both set of scores wherein they have their respected mean and standard deviation. Okay, so we could actually see that since standard deviation is the same with both the curves, so we could actually assume that if this is this distance, let's say call it A, is the same as this one. Okay? Okay. So because they have equal standard deviation. So most probably, now we could assume also that if the mean of the first curve, let's call it curve A, and then this one is curve B, the mean of the curve A or mean sub 1 is part of the what lowest scores of the or scores far from the mean or mean sub 2 of the curve B. Oh, it goes the same otherwise with curve A with respect to mean sub 2. Other instances such as this one, wherein the normal curve of let's say curve A with standard deviation sigma sub 1 and mean sub 1, and curve B with standard deviation sigma sub 2 and mean sub 2, you could actually see that they have the same mean, but this time they have different standard deviation. So the graph or the plotting of the normal curve in this case will be somehow this one. So we can actually see that the scores or since they have different standard deviation in curve B, the scores are spread out, no? Or should I say the value of the scores or the area or the probability will be different, no, from the curve A because that's different standard deviation. But the mean is the same, so therefore we could actually see that in both curves or both set of scores arriving on this normal curve, the scores are somehow similar with each other, no? So that's what we're going to that's the thing that we could observe on this curve from the illustration. So now let's have these properties of the curve because we already see different kinds of normal curves and their possible scenarios. So first of the properties of the normal curve is that the mode, which is the point on the horizontal axis where the curve is maximum, occurs at x is equal to mu. So let's go back with the normal curve. So mode in our statistics means the number of square that has been repeated. So one of the properties of the normal curve is that the mode is maximum at which x is equal to mu. This is the x-axis and this is our mean. That means that our mode is at maximum here in this portion because the mode is the repeated value on the set of scores. Therefore, as long as it closest to the mean, let's say this one, say let's assume this area. This area almost had the same scores, no, with respect to your mean. So let's say your mean is 50, then this one, let's say 49.9, and this one is 50.1. So all the scores are almost the same as long as it gets near the mean. No, at x is mu. Okay? So that's the first property. Next is that the curve is symmetric about a vertical axis through the mean, or what we call symmetrical. So let's go back here. So we could actually see that the area on this one, let's call it area 1, is the same as the area on the left or right side of the mean, which is area 2. So they are the same. No? That's why it's called symmetrical. So next, the curve has its points of inflection at x equal to mean plus minus sigma. It is concave downward if mean minus sigma is less than x, but x is less than mean plus sigma. And it is concave upward otherwise. So when you say concave upward, So the scenario will be mean minus sigma greater than x, but x is greater than mean plus sigma. Okay, that is the other side, which is concave upward. Okay, so that's the second or third property of the normal curve. The fourth one is that the normal curve approaches the horizontal axis asymptotically as we proceed in either direction away from the mean. So let's go back with the normal curve. So we could actually see here, okay, in this case, no, the curve or the curve of the function, let's say f of x, as it approaches the horizontal axis x, it approaches in such a way that the curve is asymptotically related or approaches the x-axis. So when you say asymptotically, that means it will never touch the axis. Okay? They will never meet. There's no intersection. Okay? That is from the idea from your algebra, no, the vertical asymptote and horizontal asymptote of the functions. Okay? So the same thing with the normal curve. And then last is the total area under the curve and above the horizontal axis is equal to 1. So the same idea that we have, if you still remember, with the probability distribution function or PDF. So let's say this is f of x, the curve. So to find the area of the curve, no, or below the curve and above the horizontal axis, we could actually use the idea of from your algebra or calculus in finding the area under the curve, that is equal to the integral of f of x dx, ranging, let's say, from a to b. But in this case, we're talking about the whole normal curve. So given that x is, or let's say x ranges from negative infinity to infinity, therefore the same thing with the probability distribution, we actually say that the integral of f of x dx ranging from negative infinity to infinity is equal to 1. And that applies also with the p property, that the area under the normal curve and above the horizontal axis is equal to 1. Therefore, the area to the left of the mean is 1 half, and the area to the right of the mean is also 1 half. So, in percent, that is 50% on the left and 50% on the right. Okay? So, that's the properties of the normal curve. Now, since we're talking about the area, let's let's look at this one. The curve of any continuous probability distribution or density function is constructed so that the area under the curve bounded by two ordinates x sub 1 and x sub 2 equals the probability that random variable x assume a value between x sub 1 and x sub 2. So in this case, what we're going to use is the density function of the normal distribution. So the equation that was been presented a while ago. So the same thing with computation of the area or probability under the normal curve. So we're also dealing with or using the same equation that we have. No, that the probability of x less than x sub 1 and greater than x sub 1 and less than x sub 2 is what? The integral of f of x dx ranging from x sub 1 to x sub 2, wherein your f of x is the equation presented a while ago, the density equation. So you could actually see here that applying the concept of integration, we could reduce it, or should I say presented it in this manner, no? That 1 over square root of 2 pi multiplied by sigma multiplied by the integral of e raised to negative 1 over sigma squared, 1 over sigma squared, 1 half over sigma squared, and then multiplied by x minus mean squared. Okay, dx. So, from that, no, let's look at the normal curve. So, x sub 1 and x sub 2 here, let's say in this one. So, the area of the shaded region is the one that we are going to compute, or the probability. Okay? So, we could actually assume that the probability, let's say, assuming that the area from the, assuming that the area of the full curve is 1, and if they have respected a sub 1 and a sub 2, which is to the left and to the right of the normal curve respectively, we have that 0.5 and area sub 2 is 0.5. So at least we could have the idea that this area could be greater than zero point 0.5 but actually less than 1. Okay? So in this case, that's from the for the normal curve. How about in this one? So we can actually see here that we have two different normal curves, but the area bounded by curve A, which is to the right of x sub 1, is part of the area bounded by curve B, which is in between, let's say, x sub 1 to x sub 2 of this curve. So in that case, now, since we're dealing with areas to the left or areas to the right as presented a while ago with the normal curve, we could actually use, no, transformation of the x values because it's hard for us to compute if the scores are presented in a normal distribution or in a normal curve. So how we're going to transform the x values or the scores so that we can actually see or compute or calculate the values of the probability. So in transformation of the values of x, no, in a normal curve to a new set of observations of a normal random variable z with mean equal to 0 and variance equals to 1, this is the general equation. So z is equal to x minus mean over sigma. Okay? So applying this, no, concept that z is equal to x minus mean over sigma, we could actually substitute that from the previous equation or probability density function. So let's substitute this one. No, let's write it this one. Z is equal to x minus mean over sigma. Therefore, if z has been squared, no, z squared is x minus mean squared over sigma squared. So we could actually substitute this one with z squared. You see this? Okay. So you actually that with z squared, and then it arrives to this one. Therefore, the function that we are talking about here, no, the probability that x greater than x sub 1 and less than x sub 2 will be the probability of z ranging from z sub 1 and z sub 2. Okay? The distribution of a normal curve or normal random variable with mean 0 and variance 1 is called standard normal distribution. Okay? If we're going to use z values, what we're dealing with is the standard normal distribution. Okay? So for us to appreciate this one, let's answer a problem. Given a standard normal distribution, find the area, the curve that lies A to the right of Z, which is equal to 1.84, and B between Z negative 1.97 and Z equal to 0.86. Okay? So, in presenting it in a curve or a normal curve, we could actually have this one. Okay? So, first, what the problem wants us to answer is the area on the right of 1.84. Let's call it P sub 1. Okay? So that's the first one. Let's answer letter A. So for us to answer this as presented, because it is in Z value, we're going to use the Z table for areas under the normal curve. Okay? What you're seeing here are the values of the Z ranging from 0 to negative 3.49 and 0 to 3.49 positive. Okay, so that means negative 3.49 to 3.49. Okay, so let's say now we want to find the area or the probability for, let's say, 1.0. Okay, let's look at the table. So on your left, or the left table are the negative ones, so that we could actually have it somehow similar to, let's say, from your Cartesian plane, no, from the x and y axis to the 0, to the left of 0 is negative and to the right of 0 is positive. So let's say for positive 1, so let's look at this one. Okay, so I will mark this the positive one. Then that's the z value. So positive 1 or 1.0. So the numbers here, no, 0.00, 0.01, are the numbers that will be added to your z value as required. Let's say 1.0. So your area is 0.8413. If it is 1.01, that is 0.8438. Okay? So with this one. Okay? So now, this area, by the way, are projected to the left of this z value. Okay? So, the 1.0 area, 1.z value has an area of 0.8413 or probability 8413 to the left of that z value. Okay? So that's the concept of this z value. Or let's say negative 1.55. So let's have here negative 1.55. Negative 1.5. Since we want to have 0.05 additional because it is 1.55. So look at 0.05 here. And then we could have 0.6, sorry, 0.0606. That is to the left of negative 1.5. Okay? So let's go back to the illustration a while ago. So we could actually answer it. So 1.84. So we could actually assume that the area on the left, no, as P sub 2, let's say. So for us to find the area to the right of the curve in question 1.A, P sub 1 is equal to 1 minus P sub 2 because one of the properties of the normal curve is that the area under the curve and above the horizontal axis is equal to 1. So P sub 1 is equal to 1 minus. So let's go back to the table. That is 1.84. So let's look at 1.8 here on the right side, no, or the right table part. So 1.8, and then let's look for 0.04. This one. So that is 0.9671. Okay, that is 0.9671. So let's write it here. 0.9671. So our answer is 1 minus 0.9671. That is 0.0329. So this is our answer. Okay? So that is the answer for that question. 0.032. So in illustration, you can actually see that 96% or almost 97% are the P2, no, the area on the left of 1.84, and to the right is 3.29% or 0.0329. Okay. So how about the other one? No, we have here the negative 1.97 and positive 0.86. So just like I've said earlier, the table of in the table of values of areas under the normal curve, those areas of probability are to the left of that z value. So we have here the z value for negative 1.97. The area on the 1.97 z value is, let's call it P sub 3. And then the area on the left of 0.86 is, let's say, P sub 4. So the shaded area here, let's call it P sub 5. Okay. In order for us to compute that, P sub 5, because that's the one that we're looking at is P sub 4, which is the area on the left of 0.86 minus P sub 3. Okay? So now let's look with the to the left of 0.86. So here, 0.8, and then let's find 0.06. This table, that is 0.8051. So, okay, 0.8051 minus to the left of negative 1.97. Let's go back. Negative 1.9 here, and then 0.07. So on this one, that is 0.0244. Okay, 0.0244. So 0.8051 minus 0.0244. That's equal to 0.7807. This is the answer. Now that for number 1 point B. Okay? So your RP sub 5 in this case. So that's the answer for problem number 1. Okay? So using z value, no, given our z, using z value given in the z table, areas under the number graph, we actually see there is a probability with respect to z values, but those values are to the left of that z value. Okay? So now let's answer problem number 2. Given a standard normal distribution, find the value of k such that a, the probability of z greater than k, that's 0.03015, and the probability of z greater than k but less than negative 0.018. So how we're going to look at that? Okay. So first, let's have the in illustration. We could actually have this one. Okay. So first assumption is that z, no, as presented a while ago, z is greater than k. So, we could actually see here that what z value is somehow greater than k. So, if that's the case, that is to the right of that k value. So, this one. So, assuming that it is on the positive side first, let's assume first. So, let's put it here, on the positive side. So, now, to find the value of k, let's call this value 0.3015 as P sub 1. Let's call it P sub 1. And then let's call it again, this one on the left side, P sub 2. So for us to find the value of k, first let's find the value of P sub 2. Because that will be the basis of our value of k on the z table. Okay? So that is 1 minus P sub 1 or equal to 1 minus 0.3015. Okay? So 1 minus 0.3015 is equal to 0.6985. Okay, that is 0.6985. That is for P sub 2. Now, let's find the corresponding K value on the Z table. So, 0.6985. So, in this illustration, we are talking about on the positive Z values. No? Let's assume first. So, let's look at 0.6985 on the right side of this slide, where in the positive values lies, z values lies. So 0.6985, I guess we could actually see in between, let's say, zero point 0.4 and zero point 0.5. So let's look at 0.5 first, no? So that is 0.6985. So 0.6985. So I think this is 0.5 and then with point, 0.02. So that is positive 0.52, which is our z, or let's say in this case k value. Okay, so this is our answer. So k here is 0.52. Okay, so that's our answer for that. Okay. Now the other one, given the area between k and negative 0.18 as 0.4197. So in this time, let's call it p sub 3. Okay, the area to the left of k, let's call it P sub 4, and the area to the left of negative 0.18 as P sub 5. Right? So, in order for us to find the value of P, let's say P sub 4, we have to, what? For P sub 4, because that's the area that we need, no? Because K value, the probability on the Z table are to the left of Z value, right? So, in this case, letter K. So, we have to find P sub 4 that's equal to P sub 5 minus P sub 3. Okay? So P sub 5 is to the left of negative 0.18. So we look at again at the Z table that is negative 0.18. So this is negative 0.1. And then look at the 8 on the column 0.08. We have 0.4286. Okay? 0.4286. That is 0.4286 minus 0.4197. So that will be the value of your P sub 4. That is 0.0089. Okay. So now, since this is P sub 4, let's find P 0.0089 on the Z table. So we could actually assume here that it's on the negative Z value. So look at again on the left table or where lies the negative value. So let's look at the 0.0089. So I think let's look first on the upper portion of this table. So 0.0089, maybe it's between negative 2.4 and 2.5. So let's start with 2. Okay, so let's start with 2.4. So 0.0089. So in 2.5, okay, there's no value. Okay. So in 2.3, so I guess we have here in 2.3, negative 2.3. So 2.3 and then on the column 0.07. This one. Okay. That is 0.0089. Therefore, that is negative 2.37. Okay. Your K value here in letter B is negative 2.37. And this is our answer. Okay. So on the first one, we have the given value z and we are asked to find the probability. But in this one, we have given the probability and we are asked to find the value of z. Okay. Now, for us to have be, for us to be familiar more with the computation regarding normal distribution, let's answer the third problem. So here it's stated that given a random variable x having a normal distribution with mean is equal to 50 and sigma is equal to 10, find the probability that x assumes a value between 45 and 62. So here, what we have is the mean, standard deviation, and x values, which is 45 and 62. So let's look at the value. So let's write it. So the mean is 50, sigma is 10 or standard deviation, x sub 1 is 45, and x sub 2 is 62. Okay? So, for the graph, that will be this one. So here, no, we have here negative 0.5 and 1.2. That is for z value. So now, let's confirm if this is right. So, let's compute for z sub 1. That is equal to x sub 1 minus mean over standard deviation. That is equal to 45 minus 50 over 10, or that is negative 5 over 10, or negative 0.5. And then c sub 2 is 62 minus 50 over 10, or this is same as x sub 2 minus mean over sigma. Sorry, right? Then that is 12 over 10, or this is equal to 1.2 positive. So the same with this graph. Okay? Or this in the normal curve. This is z values already. No? This is z value. So given these z values, so for us to compute, let's call it p sub 1, we have to find the area on the left of negative 0.1, which is p sub 2, and the area on the left of positive 1.2, which is p sub 3. So for p sub 1, that will be equal to p sub 3 minus p sub 2. Okay? So what is the area on the left of 1.2? Positive. So let's look at the table again. So 1.2. So look at 1.2. Here that is equal to 0.8849. Okay, so that is 0.8849 minus to the left of negative 0.5. So look at the table again, negative 0.5, that is equal to 0.3085 minus 0.3085. So subtracting these two values, that is equal to 0.5764. So this is our value to this P sub 1, or the probability that assumes what? X values between 45 and 62 with mean 50 and standard deviation equal to 10. So that's our answer for this problem. So now, let's move with this fourth problem. Okay. So, given the normal distribution with mean is equal to 40 and sigma of standard deviation equal to 6, find the value of x that has A, 45% of the area to the left, and B, 14% of the area to the right. So, let's look at this one. So somehow this will be the illustration. So when you say 45%, that is 0.45. No, that's the first one that has been asked here. That is 45% on the right, no, and then 14. On the left, and then 14% on the right. Given the mean as 40 and sigma or standard deviation as 6. So what we're going to do here is find first, no, what we're asking here is the z value for letter A and then z value for letter B. So given the area to the left, that is 0.45, so we can actually use the z table. Okay, so let's find the area, or let's say the probability, that's 0.45, which is assuming that is on the left. So let's assume that is from the negative side of z value. So that is what? 45%. So looking at this table, okay, so we could actually look at on the bottom part of the table. So that's from 0 to negative zero point 0.4. No? So let's check first if there's an existing 0.45. Okay, so let's start with negative zero point 0.1, I guess, no? Negative zero point 0.1. Okay, so 0.4602, 0.4562, and we have here 0.4522. Oh, we could have this one also. And then 0.4483. So the the possible values of z here is negative 0.12 and negative 0.13. So now let's write it on this one, on the other, or let's go back with the graph. So for if z value is negative 0.12, the probability is 0.4522. But if the z value is negative 0.13, that is 0.4487, right? Here on the table, or 83, 4483. So in the graph, no, what what the problem asks is 45% only of the area to the left. So if we're going to look back on the value, so both of them are almost 45 or 45% or 0.45. But the other one, which is in z is equal to negative 0.12, exceeds 0.0022, or should I say 0.22%, no, for the value. Therefore, what we're going to take is the value that doesn't exceed 45%, but almost the same or equal with the 45%. Therefore, our z sub 1 here, given 45% to the left, is negative 0.13. Or it has a probability or value from the z table 0.4483. or almost 0.45 or 45%. Okay? That's the answer for this problem. Or let's say 4.8. Okay? So, how about letter B? So, for letter B, given the area to the right, which is 0.14, therefore, on this side, no, that is 1 minus 0.14 or equal to 0.86. So now, let's find the values from the z table, 0.86 or almost equal to 0.86. So let's assume that it will be on the positive side based on our illustration. So 0.86. So we could actually start by finding on the in between 1.1 and 1.2 because it or 1.0 rather to 1.1 and 1.2. Let's look at these three. So first let's have for 1.0. So 8413, 8438, 84161, 8485, 8508, almost here. 8554, we have here. 8577, and then we have 8599. Okay. I guess this will be the closest one to 8.86. So that is 1.0 and then from the column 0.08. So therefore the value using the z table is 1.08. Therefore our z value here for z sub 2 is 1.08. Now given it has a probability from the z table as 0.8599 or almost to 0.86 or 86%. That is to the left. But given to us is the probability to the right, which is 14% or 0.40. Okay? So that's the answer for our problem. Now, let's proceed to the next one. Here, given a problem applying to practical, or should I say, real life scenario. States here that an electrical firm manufactures light bulbs that have a life before burnout that is normally distributed with mean equal to 800 hours and a standard deviation of 40 hours. Find the probability that a bulb burns between 778 and 834. So given to us the value of our mean, which is 800, our standard deviation equals to 40, and then we have x sub 1 as 778 because that's where asked not to find out the probability between 778 and 834. So x sub 2 therefore is 834. Okay, so that's the one that we're going to compute. So in illustration, so somehow this will be the illustration for the normal curve. Okay, so given to us are x values, so let's transform it to z values, right? So for z sub 1, that is 778 minus 800 over 40. Okay, that is equal to negative 0.55. Okay, for z sub 2, I will write it here on the right side, that is 834 minus 800 over 40 or x minus mean over standard deviation. That's equal to that is positive 0.85. Okay. So you can actually write it here negative 0.55 and positive 0.85. So we're asked to find this shaded region. Okay. For us to find out, let's call it P sub 1. So to the right of negative 0.55 is P sub 2, let's say, and then to the left of the 0.85 is P sub 3. So therefore, to find this value, P sub 1 is equal to P sub 3 minus P sub 2. Okay, so what is to the left of negative, or sorry, 0.85 first, positive 0.85, that is 0.8 here, and then 0.05 one. So that is 0.8023. Okay, 0.8023 minus P sub 2. Okay, that is to the left of negative 0.55. Okay, so let's go back here. Negative 0.55, 0.5 negative. And then, let's go find the column 0.05. I think it's here. 0.2912. Okay, minus 0.2912. So, P sub 1 is the difference between those two values. That is 0.5111. So, this is our answer on this problem. Okay, so that's the answer for our problem. 0.5111. Given our x values are those are in between 778 and 834. Okay? So for our last problem, we have this one. States here that in industrial process, the diameter of a ball bearing is an important measurement. The buyer sets specifications for diameter to be 3.0 plus minus 0.01 centimeters. The implication is that no part falling outside this specification will be accepted. It is known that in the process, the diameter of a ball bearing has a normal distribution of with mean is equal to 3.0 and a standard deviation of 0.005. So we could actually observe that the standard deviation is less than 1. So therefore, the distribution of the scores, or let's say specification or values, is somehow close to the mean. Okay? On average, how many manufactured ball bearings will be scrapped? So let's answer it by finding the x values for the problem. So, given the specification 3.0 plus minus 0.01 cm. Right? So, therefore, we could actually have that x sub 1 as 2.99 and then x sub 2 is 3.01. Okay? So, given the mean as 3.0 and standard deviation as 0.005. Okay. So, from here, we can actually compute for z sub 1 and z sub 2. So, z sub 1 is x sub 1 minus mean over standard deviation, or equal to 2.99 minus 3.0 over 0.005. That is equal to negative 2.0. So, therefore, in if c sub 2, that is x sub 2 minus mean over standard deviation, somehow the same because the parameter is 3.0 plus minus zero point zero 0.01. So 3.01 minus 3 over 0.005, or this is equal to positive 2.0. Okay? So if we're going to graph it, in such a way, using normal distribution, we could have this one. So let's say this is the 0, and then we have this negative 2, we have the positive 2. So the area that in between negative 2 and 2 are those that are what? Accepted. Okay, because it lies on the specification given, that is 3.0 plus minus 0.01. But those outside this one, or this one, the shaded in red, are the ones that are scrapped or rejected. So now let's find first the area to the left of negative 2. So let's call it P sub 1. Okay, P sub 1. So area to the left of negative 2 using the Z table. So let's look at negative 2. That is here. And then that is 0.0228. Okay, 0.0228. So 0.0228. So it follows, since they both have the same uh, numerical value of z but different sign or location, Therefore, we can actually conclude that this one, p sub 2 for positive 2 is the same as, or to the right of 2 is the same as 0.0228. Okay? So, to confirm that, let's find the value of to the right of p sub 2. Let's call it p sub 3. That is, for us to find the p sub 2, therefore 1 minus p sub 3, or this p sub 3 is the value to the left of 2. So that is, let's find it, 2 here in the table. That's equal to 0.9772. So therefore, that is 1 minus 0.9772, or the same as 0.0228. Okay? So, what the problem asks us is to find the amount, no, of those scrap that has been manufactured that day. Okay? Not complying with the diameter or specification of the ball or bearing ball, that's 3.0 plus minus zero point zero 1 centimeter. So therefore, for the amount, let's say, let's call it M, that is P sub 1 plus P sub 2, no, this sum multiplied by 100%. Okay, that's equal to, no, 0.0228 plus 228 plus 0.0228, okay, multiplied by 100%. That's equal to 4.56%. So this is our answer for this problem, or the amount of ball that will be scrapped. Okay? So that's the end of our discussion for today.